Suppose the landowner gives you 100 meters of fencing and tells you that you can take any region of his land that you manage to enclose with this fencing. What path should you follow as you lay down the fencing so that the area of the region you obtain is maximized? This kind of problem is known as an optimization problem. More explicitly, we have a very large, even infinite set of options or possibilities, in this case the shape of the closed path, and we want to determine an option which maximizes a certain quantity, in this case the area of the enclosed region. At this moment, it is probably quite clear that this problem, stripped of its physical aspects given merely for presentation, is entirely mathematical in nature, and can be restated in slightly more formal terms as follows. Among all the closed shapes with a given perimeter L, find the one that has the greatest area. In fact, it is a rather classic question known as the Isoperimetric Problem, with evidence of early investigations found in the works of ancient Greek mathematicians such as Euclid and Archimedes. Archimedes in particular is said to have posed the problem around the 3rd century BCE, and is recognized for making significant advancements in its study. Over the subsequent centuries, mathematicians' attempts to wrestle with this problem did not cease, and while they were able to offer valuable insight and conjectures, it was until the 19th century that a rigorous proof for its resolution, published in 1838, was provided by the Swiss mathematician Jacob Steiner. His elegant geometric approach inspired further developments in geometric inequalities and optimization theory. We can similarly motivate the isoperimetric problem together with other related problems in the legend of Queen Dido. Fleeing the tyranny of her brother Pygmalion, the Phoenician Dido, together with a group of inhabitants of the city of Tyre, began heading westward along the coast of the Mediterranean in search of happiness. They would eventually decide to settle near the African coast around what is now the Gulf of Tunis. This unwelcome arrival did not, however, seem to appeal to the inhabitants of the area. Nevertheless, Dido managed to persuade the chief, who was naive enough to grant Dido a patch of land which can be encircled by an ox's hide. It was only later that the trick of the Phoenician became evident, having cut the ox's hide into thin strips. She tied them end to end, forming a long rope which allowed her to delimit a considerable piece of land, on which she later founded the city of Carthage. All these events were reported by legend on 825 BCE. Analyzing this situation, we can see that the isoperimetric problem appears when Dido is to decide how to lay down the rope to obtain the largest possible region of land. Going back to our problem, it appears we are having some difficulty with the notion of a shape. Mathematically speaking, it is not clear exactly what it means, and so we come to the realization that we will need to develop some tools first to tackle this problem. This naturally leads us to the theory of curves, or in our particular case, the theory of planar curves. Planar just means that the curves we will study are embedded in the 2D plane. So what is a curve? Well, a parametric planar curve is a mapping or a function, say gamma, from an interval I to R2. R2 of course is just the Cartesian product of R, the set of real numbers with itself, so this mapping associates to each t a vector. To write it using the functions we already know how to work with, which are the ones that go from the real numbers to the real numbers, we can say that this vector has components xt and yt, where x and y are both functions that go from the interval I to R. This definition alone isn't enough though, and we need to add what's called a regularity condition. The most basic is to at least require the functions x, y to be continuous, because a curve that jumps in space, well, isn't really a curve. Usually, however, we further require x and y to be of class CR, where r is a non-negative integer or infinity. When r is a non-negative integer, this just means that it's r times differentiable and its rth derivative is continuous. And when r is infinity, so class C infinity, it means that the function is k times differentiable for all k and n. Another regularity condition is often imposed when r is greater than or equal to 1. That is, gamma prime of t is not 0 for all t and I. Well, at each instant t, the vector x prime of t and y prime of t represent the tangent vector or the velocity vector. So with this condition we make sure that while moving along the curve we never freeze in place, so to speak. And in particular, since x prime and y prime have to be continuous, then we never change direction. We just want to trace out the curve smoothly in one direction as t runs through the interval I. To fix one definition, we will define a regular parametric planar curve as a function that goes from an interval I to R2, that is of class at least C1, and such that gamma prime of t is different from the zero vector at each instant t. Note that in practice, however, we will omit the words regular, parametric and planar, and any curve we mention from now on will be considered regular unless otherwise stated. Now, let's quickly see an example. The unit circle in R2. We want to apply our definition and find a parametric curve whose image is the unit circle. If we take the interval I to be 0 to pi, this is as simple as taking the x component to be cosine of t and the y component to be sine of t. The parameter t can be thought of as representing time. We say that gamma is a parameterization of the unit circle. In addition to the previous definition, we may also sometimes require curves to be simple. A curve is called simple when it does not intersect itself. In other words, for any t1, t2 and I, we have gamma of t1 is not equal to gamma of t2, or equivalently, gamma is injective. Now, the curves we are interested in this problem are the closed ones. A curve is said to be closed when its initial point and its final point are the same. Formally, it must be defined on a closed interval I, which is equal to AB, and satisfies gamma of A equals gamma of B. Notice that when a curve is both closed and simple, we run into a bit of a problem. The earlier definition for simple curves no longer works, because since the curve is closed, we have A is not equal to B, but gamma of A is equal to gamma of B. So we'll need to modify the definition of simple curves. This is easy to fix though. We only need to make one of t1 or t2 belong to the open interval AB instead of the closed one, and that would eliminate the issue. Next up is the notion of orientation. A closed curve is said to be positively oriented when, if we consider an observer tracing out the curve, the interior region of the curve is always to the left of the observer. Otherwise, it is said to be negatively oriented. Just a quick recap on what we've seen so far. We've defined curves to be functions from intervals to R2 that are of class C1 and whose velocity vector is always non-zero. We said that it's called simple when it does not intersect itself, closed if the initial point equals the final point, and positively oriented, in this case of closed curves, if its interior region is always to the left of an observer tracing it. Next, let's see the notion of rectifiable curves. Let gamma be a simple curve and take n distinct points from the interval AB. The set P containing the images of these points by gamma defines an inscribed polygonal path. Let's write down the rest of the definition and we will break it down slowly. So the idea is to sample n points on the curve and connect them with straight line segments to obtain an inscribed polygonal path. We then add up the lengths of these segments to obtain the length of the polygonal path L of P. To understand the formula, observe that this vector here, for example, is gamma of S2 minus gamma of S1. We then take its Euclidean norm, which is the usual distance we know in the plane calculated using the good old Pythagorean theorem. What we are saying is that the curve is rectifiable if there is a positive constant m that bounds the length of all polygonal paths inscribed in gamma, no matter how large n is or how we sample the points on the curve. Of course, provided the first and the last point we sampled are exactly the endpoints of the curve, and as we add more and more points that are more or less evenly spaced, the length of the inscribed polygonal path should approach what we expect the length of the curve gamma to represent. This, in fact, is what inspires the following definition. If gamma is a simple rectifiable curve, then the arc length of gamma is defined as the supremum over p of L of p, in other words, over all the possible inscribed polygonal paths. This expression, however, isn't very useful and does not give us a way to calculate the arc length. Hence, we have the following proposition, which we will not prove. Let gamma be a simple rectifiable curve, then the arc length of gamma is given by the following formula. While the following is not a proof, it can perhaps help to see why this result holds. Going back to our previous visualization, if we label the change in x between two consecutive points delta x of k, and the change in y as delta y of k, then the length of this inscribed polygonal path corresponds to adding up expressions of this form. We can rewrite this equivalently by introducing the change in t as well as making some simplifications. Now, as we add more and more points and the quantities representing change approach 0, roughly speaking, the sum becomes an integral and the delta something becomes d something. Now for the area, let gamma be a simple closed positively oriented curve. The area enclosed by gamma is defined directly as the following integral. Again, for intuitive understanding of why this should in fact give the area, one can employ a similar process as before. Recall that we gave earlier the expression for the arc length along the entire interval AB, but notice we can also consider L as a function of t, where the integral goes from a to t instead of all the way to b. This gives us, so to speak, how much of the length of the curve we've covered so far at any instant t. Now, we say that a curve is parametrized by arc length if at any instant t the parameter t itself represents the arc length. Another proposition that we'll not prove is that any simple curve can be parametrized by the arc length. A proposition we will prove, however, is the following. Let gamma be a simple curve parametrized by arc length, then the Euclidean norm of the velocity vector is always equal to 1. For the proof, just write down what it means for the curve to be parametrized by arc length. And then notice that since the derivatives of x and y with respect to t have to be continuous, since the curve is of class C1, we get after composition with other continuous functions that the whole integrand is continuous. The fundamental theorem of calculus tells us that this function of t is then differentiable, and its derivative is equal exactly to the integrand function evaluated at t. The derivative of the right side is just equal to 1, so if we differentiate both sides of the equation, we get our result. So now we have the necessary tools, we can actually restate the problem properly. Among all simple closed planar curves of length L, determine those that enclose the largest possible area if such a maximum exists, of course. Notice that up to this point, we haven't actually stated the answer. So let's do that now. You might already know it is in fact the circle. That is, among all simple closed planar curves of length L, the circle of perimeter L encloses the largest area. But in fact, we have an even stronger result known as the isoperimetric inequality, which states that for any simple closed curve gamma of length L and that encloses area A, the square of L is larger than or equal to 4 pi A, with equality if and only if gamma is a circle. This implies the previous statement because for a fixed value of L, the area A is bounded by this quantity, which depends on L. So A is at its largest when there is equality here, which we claim is the case if and only if gamma is a circle. First, note that plugging in the formulas for the arc length and the area and trying the usual integral inequalities doesn't work and leads us the wrong way, providing an upper bound on L rather than a lower bound, which is what we are after. Hence, we will need to use a different approach. So let gamma be a simple curve. And to simplify things, we will fix the interval to be 0 to pi. Our journey begins by calculating the following integral, which looks like the formula for the arc length, but without the square root. In other words, rather than the norm of the velocity vector, we integrate its norm squared. To do this, we utilize the arc length parameterization. Set t to be equal to twice pi over L times s, where s is the arc length parameter, which we are allowed to do because, as we said, every simple curve can be parametrized by arc length. So we get that when t is equal to 0, we have s is equal to 0, and when t is equal to 2 pi, s is equal to L. Also, as goes the usual change of parameter procedure, we find the value of dt and also express dx over dt using s. And the same for dy over dt. Replacing in the original integral, taking out common factors and simplifying, we end up with the following. But since s is the arc length parameter, notice that this expression here just evaluates to 1, as demonstrated earlier. We thus find that the value of the integral is L squared over 2 pi. This in particular allows us to express L squared as an integral, which will be very useful. In case you've forgotten, the isoperimetric inequality we want to prove is L squared is larger than or equal to 4 pi a, or equivalently, L squared minus 4 pi a is larger than or equal to 0. So we plug in the formula for L squared we've just obtained together with the formula for the area to get the following form. We then collect these two terms as a sum squared, which also gives us an additional y squared term that we subtract again. Note that this term here is clearly always non-negative, so the inequality will be proved if we show that this term is non-negative. However, this isn't true in general. For example, if y is a non-zero constant, the square of the derivative of y minus y squared is equal to minus c squared, which is always negative, so the integral of this over 2 pi will also be negative. Nevertheless, if we add additional conditions, we can obtain this result. This is in the form of Wirtinger's inequality, which states that if y is a differentiable function from 0 to pi to r such that its integral is 0 and y of 0 is equal to y of 2 pi, then the integral of the derivative of y squared is greater than or equal to that of the function squared, with equality if and only if y is equal to a cosine of t plus b sine of t. Perhaps the simplest way to prove this is using the Fourier expansion. All you need to know is that given certain conditions are verified, and in this case they are, a function has an expansion as a series of sine and cosine terms. The sequences an and bn are called the Fourier coefficients of y. Now, because of the way a0 is defined, it just equals 0 by hypothesis. Next, a useful result known as Parseval's formula allows us to express the integral of y squared, and the integral of the derivative of y squared using the Fourier coefficients of y, which is exactly what we need in this case, since the general term of this series is always non-negative. The inequality is proved. Furthermore, since the first term is equal to 0, we can start the series from n is equal to 2 instead. And when this infinite sum of non-negative terms is equal to 0, all of its terms must be equal to 0. Notice that this term here is never 0, so it must be this term that is always equal to 0. This gives that an is equal to bn, and both are equal to 0 for all n larger than or equal to 2. Which, if we plug back into the original expansion, gives us that y is equal to a1 cosine of t plus b1 sine of t, demonstrating the equality case and ending the proof. To apply this result to our problem, note that the integral of y doesn't always have to be equal to 0. Nonetheless, if it is different from 0, we can always apply a suitable translation by setting y tilde of t to be equal to y of t minus y0, where y0 is the integral of y over 0 to pi. We also define a new curve gamma tilde by replacing y with y tilde. Note that the translation is an isometry which preserves distances. In other words, gamma tilde has the same length and encloses the same area as gamma. Also, y tilde satisfies the conditions for Wirtinger's inequality, so we can immediately apply the result, and the isoperimetric inequality is proved for gamma tilde, and as a result for gamma as well. For the equality case, so when L squared is equal to 4 pi a, we have that this integrand is always non-negative, so it must be equal to 0 at each point of the interval. The second integral is also non-negative, so it must be equal to 0 as well. Applying the equality in case of Wirtinger's lemma, we get that y tilde is equal to a cosine of t plus b sine of t. And for the first equation, we obtain that x is equal to minus the integral of y tilde from 0 to t plus a constant. Since we already have the expression for y tilde, we can integrate directly to obtain the expression for x. Finally, at each point t, if we calculate the distance squared between gamma tilde at the point x0, 0, we find that it's equal to a squared plus b squared, a constant that does not depend on t. This is to say that gamma tilde is a circle of center x0, 0 and radius square root of a squared plus b squared. This proves the equality case, and so the isoperimetric inequality as a whole is proved. To get a little further in the reasoning, we go as far as to claim that Wirtinger's inequality is actually equivalent to the isoperimetric inequality. The first implication, that Wirtinger's inequality implies the isoperimetric inequality, is already seen, so let's do the reverse implication. Suppose the isoperimetric inequality holds for all closed curves. Then, in particular, it holds for a gamma such that the following holds. y0 is equal to y of 2 pi, the integral of y is 0, and x of t is written as minus the integral from 0 to t to y. Notice that x of 2 pi is equal to 0 by hypothesis, which also equals x of 0. This gives us that gamma is indeed closed. By the isoperimetric inequality, L squared minus 4 pi a is larger than or equal to 0, which we write in the form we derived. And because of the way x was defined, the first term is just 0, so we are left with exactly the statement of Wirtinger's inequality. This concludes the proof. We thank you very much for your attendance, presence and attention, and we hope you found this problem as interesting as we did. And we also hope that you learned something from this presentation.